Good morning, everybody. Today's Physics Talk Model 1 is on speed and braking distance. So this is part of Chapter 1, Section 5. Make sure you take good notes. Most of you have already done this in class. This is really for the people who have been absent. So our learning objective is to understand negative acceleration for braking distance. Your job is to analyze and interpret data to make sure we can do that, and then recognize patterns, and of course with any number calculations we do, scale, proportion, and quantity. Sorry about all the background noise. Reminder from the chapter challenge, you're expected to explain what factors affect following distance, braking distance, and the total stopping distance. Our focus on this one is actually the braking distance. And negative acceleration helps us understand braking distance. In general, of course, acceleration is a change in velocity with respect to change in time. And of course, this is our formula from before, and it's still the same formula. It's just now that our final velocity when it comes to braking distance probably approaches zero or goes close to zero. Now, negative acceleration, it's basically a change in velocity with respect to time of an object. And there's really two ways to actually handle this. You either have a decreasing speed in a positive direction, or you have an increasing speed in the negative direction. And what it really comes down to is you really need to pay attention to which direction is your acceleration pointing and which direction is your velocity pointing. And the idea is if your velocity is positive and your acceleration is negative, that means the object that you have will actually slow down. This is where we talk about that decreasing speed in the positive direction. On the other hand, if your velocity is negative and your acceleration is also negative, then the situation happens where you're actually going to speed up going backwards. This is a case where you pass the friend's house, and of course now you need to back up. You stop and you speed up in the backwards direction. Your acceleration is going to be backwards, so that means your speed will increase. Another situation is, oh, my velocity is this way, but now I got to slow down again because I'm about ready to park near my friend's house. And then you press on the brake. Well, that means your acceleration is positive, but since your velocity is opposite direction as your acceleration, that means you're going to slow down again. That's where you're slowing down and coming to the rest in front of the house. And then later on, maybe after you parked, decide, okay, it's time for me to leave. And you speed up in this direction, and your acceleration is pointing in that same direction. So that means if they're pointing in the same direction, that means your speed will increase. And so these are the things you got to pay attention to. In general, if they're pointing in the same direction, you're going to speed up. And if they're pointing in the opposite direction, you're going to slow down. All right, so our newest equation, because of our lab, is the VF squared equals 2AD plus VI squared. This is really what we call the no-time formula. And it's really useful whenever time is not given in the problem and you're given final velocity, distance, and initial velocity, and you need to find the acceleration. Or maybe you're given the acceleration, initial velocity, and final velocity, and you're trying to find the distance. Or you're given acceleration, distance, and initial velocity, and you want to find the final velocity. So this, as long as time is not given, becomes a critical formula for you to use when solving. Okay, let's look at sample problem number 1. Why don't you take some time to copy this down. A softball pitcher accelerates a ball from rest to a speed of 25 meters per second over a distance of 1.8 meters. What is the ball's acceleration? Pause, copy, and then solve. All right, so in looking at the solution, one of the things we want to pay attention to is what's given. So we got from rest, that means the initial velocity is 0. We got a speed of, what the heck happened? We have a speed of, all right, so we have rest, initial velocity from rest, and then we have a speed of 25 meters per second. That's also important. Over a distance of 1.8 meters. What is the ball's acceleration? So let's label those accordingly. VI, that's VF. This guy over here is the distance. That's the acceleration. That is what I'm looking for. So the question is, how do we solve this? Okay, so now that we've identified everything, our given on our list will be V initial is equal to 0 because rest means 0 meters per second. V final, which is over here, is 25 meters per second. The distance is 1.8 meters. And of course, I'm trying to find the acceleration. So to calculate the formula, I got to choose what formula has VI, VF, D, and A. The only one that has that is my no time formula, which is VF squared equals 2AD plus VI squared. So now I just plug it in, solving. So I have VF, I have D, I have VI. Only thing I'm looking for is A. So I'll plug those numbers in. VF is 25, and I square that. 2 times A times 1.8 meters plus VI squared, which is 0 squared. Oh, I don't even need to put my meters for now, sorry. And so when I plug that all in, I get 625 is equal to, multiply those two together, 3.6 times A. Solving for A, divide by 3.6. I plug that into my calculator and put that in there. 625 divided by 3.6 is equal to 174. So my acceleration is going to be 174 meters per second squared. And the reason I know it's meters per second squared because I remember that on my chart. Make sure you look at the chart when you guys are taking this. So sample 2. Again, copy this down first. During an auto race, a car with a speed of 75 meters per second accelerates past another car at a rate of 3.0 meters per second squared for 4.0 seconds. How far does the car travel during that time? And my suggestion is to annotate, just like I did in the last problem, but pause for now, and when you're ready, we'll go over it. So in terms of the important numbers, 75 meters per second, that's the initial speed. 4 seconds is time. 3.0 meters per second squared is the acceleration, because that's the units of our acceleration. And I want to know how far does it travel, which is a distance. So that's VI. This is acceleration. This is T. And then how far is the distance. Okay, so in sample problem 2, we identified our initial velocity, acceleration A, so I'm going to write that in my given. So given would be VI is equal to 75 meters per second. A is equal to 3.0 meters per second squared. T equals 4.0 seconds. And the question is, how far does it travel? So looking again on my formulas, I'm trying to find D, so I'll put that as a question mark. In my formulas, I have a formula that says D is equal to 1/2 AT squared plus VI times T. And the reason I picked this one is because I'm looking for D, I have time, and I have initial velocity, acceleration, and time. Acceleration, time, initial velocity, all that's covered in there, so we're going to solve it. So D is going to equal 1/2 times 3.0 times 4 squared, or 4.0 squared, plus 75 times 4.0. So again, I'm just plugging in the numbers for T. There's the 4.0 twice. That one's squared, that one's not. 75 for the initial velocity, 3 meters per second for my acceleration, and then we just plug in the calculator. So D is then going to equal, let's see, that's going to be 16. 16 divided by 2 is 8. 8 times 3 is 24. Plus 75 times 4, well, that's 150 times 2, that's 300. So then D will equal 324 meters. All right, that's the end of everything. If you have any questions, come see me tutoring.